Alright, so the segment addition length section, where we're just dealing with the lengths of random segments. And I want to make sure we talk about, when we see lengths in geometry, we're going to be talking about random lengths often. It's not going to be drawn to scale. So if I look at that segment, AB, or that segment CD, if I write 3 feet on it, that does not mean it's 3 feet. I'm just saying, let's suppose for a minute it's 3 feet, right? That's not 2 millimeters necessarily. We're just going to say, let's suppose that's 2 millimeters. We want to talk in units because we want to get used to using units, but a lot of times we'll just use a number and then we're really just talking about a generic unit. So if there's no unit written in like feet or millimeters, we can say units. But often we use feet, millimeters, inches, yards, miles, just to get in that habit of using units. Because everything we do in geometry is really building towards representing real-life things that have real-life measurement units. Those are not really 2 millimeters and 3 feet. Our first big postulate we're going to learn from it in a minute. A postulate, otherwise known as an axiom, is a rule that we agree holds true even though we can't formally prove it. We're going to deal with theorems in a few days here. Those we can prove. Postulates, we just agree they work, but technically we can't prove them. So our first postulate we're going to learn is the segment addition postulate. It comes in very handy, and you probably kind of already actually know it without formally knowing it. It just makes sense. So, the segment addition postulate says, if I have a segment AC, and on segment AC, B is between A and C, then AB plus BC equals AC. They're little plus little equals big. If it's all part of one big segment, I can add the two little parts. B has to be between A and C for that to hold true. So let's look at an example. This is a forwards example, I like to say. I have segment PQ and segment QR that make up segment PR. I know the length of PQ is 3 and the length of QR is 8. And I know you already know the answer is going to be 11. But let's go through how we're going to do it formally. Find the length of segment PR. Notice, because I'm talking about that segment over there by name, I put that segment hat on it. If I didn't put that segment hat, then we'd be talking about the length of the segment. I'm talking about the name of the segment, so I have to say PR with that flat hat. So PQ plus QR is PR. We can tell by the picture, and we know the lengths of 2 of the 3. As long as we know 2 out of 3, we only have 1 unknown, we can do the math, and we know that PR is 11. Again, you probably knew that just logically, but you're going to need to be able to justify things in geometry. So, we're going to substitute 3 and 8 in for PQ and QR. We're going to then add. But the whole reason we could do that in the first place, we need to be able to cite a postulate or theorem to work with that given information. So our first justification step there would be, well, segment addition postulate works for this type of a segment. Here's another example. I like to call this one a backwards example. Think about what's backwards from addition, and you'll remember how we did this one. So we know that CD is 4 and CE is 10, and we want to find the length of DE, segment DE. Remember, we have to say the segment, otherwise we'd be saying the length of the length. So CD plus DE equals CE. We have to start with the segment addition postulate. Then we can substitute the values we know, but this time the values we know are one of the little ones and the big one. So we had to subtract to find out that DE is 6. So our steps that we have to justify, start with segment addition postulate. I'm going to abbreviate, then we substitute. Again, I'm going to abbreviate, being very careful that I put enough letters that it doesn't look like subtract, because then I'm going to subtract. So that's how I know that DE is 6 with justification. So I mentioned this a little bit before. We're going to talk about congruence, or congruent segments. And congruence means has the same length. So if I have segment XYZ, and I want to show that Y is exactly in the middle, I can put little congruence marks, just one little tick mark, matching, sorry about that, to show that from X to Y is the same length as from Y to Z. Segment XY is the same length as segment YZ. So they are congruent. We can look at another example of a rectangle. So far, that's not enough information for us in geometry to prove that it's a rectangle, or for you to be able to assume it's a rectangle. We have to know that it has 4 right angles, and the other qualities of a rectangle, opposite sides have to be congruent. So there's one pair of opposite sides that are congruent, because we match the one congruence mark to the one congruence mark, and then 2 congruence mark matches 2. So we know those 2 vertical sides are congruent, and the 2 horizontal sides are congruent. So that's how congruence marks work. And that's the symbol that we're going to use for congruence. Equal sign with the little squiggly tilde mark above it. So we're going to say segment XY is congruent to segment YZ. Notice how that time I read segment because it was wearing the hat. We always use that kind of a notation when we're using congruence. That segment says something slightly different, and I know it sounds like I'm saying the same thing, but that one says the length of XY is equal to the length of YZ. That one's talking about actual numbers. I like to talk about the first one being like your name, and the second one being like your height or your weight or your birthday, some kind of number. Right? That one is a name. That one is, in this case, a length. So since it's a length, it works like a variable, and we can do math on it. That's why we used that when we were doing the segment addition postulate. We can add those kind of things, we can subtract them, we can multiply them, we can divide them. Most of the time we're going to be adding or subtracting them. So let's look at another little example here. I've got this big segment made up of more little segments, and that tells me that AB is congruent to BC. I can also say that AB has the same length as BC, but those would be written out differently. They're going to give us the statement that AB is equal to 3 and AD is equal to 13. So we know the lengths of a couple of these segments. Whenever I have these kinds of problems, I like to find all the lengths and then worry about what they're asking me for. In this case, it's saying find all the missing lengths. So we're going to find BC. Well, if AB is 3, then BC is 3. Okay, there's one other part that we haven't talked about. Oh, sorry, wrong order. We know that if AB is 3 and BC is 3, then together they're 6. A to C is 6. CD is 7. How did I get that 7? Well, I know the whole 13, and I know that 6. I really just did the segment addition postulate backwards there to get that 7. And then BD is all of AD except for AB, so I had to subtract 3 from the 13.